This is AQA A-Level Chemistry, Year 12 topic alcohols, and this is part 3 of the alcohol series of videos. In this one, we're going to look at how equilibrium comes into play with alcohols. We're going to look at how alcohols are made. We're also going to revisit some nomenclature and isomerism work as well. So I'm going to recommend you pause as you go, try the activities, and then see how you do. In the first instance, we are looking at the hydration of ethene. We can see here we are adding water, it's gaseous, so it's steam, and we're adding it to ethene, making ethanol. We have an enthalpy change for the forward reaction, and we're thinking purely in terms of equilibrium yield. What would your conditions be? So first of all, we would go for a low temperature, because low temperature favours the exothermic reaction, because that will try to bring the temperature back up. That is always the case in an industrial process, that we would want the equilibrium to shift to the right to give us a greater yield of product. We'd also want a high pressure, and the high pressure is because I've got 2 moles on the left going to 1 mole on the right. So increasing pressure will favour the reaction that leads to a reduction in the number of moles. Now, we might have problems here. Why might we not choose to use those conditions? You might want to think back to your knowledge of the Haber process and the work done on equilibrium with that. And the low temperature, it might be that the rate of reaction is just too slow to make it feasible. And a high pressure is great, but you've got to make sure that the machinery, that the vessels are reinforced so that they can withstand the higher pressure. So actually the conditions that we take are very much a compromise. Temperature of 300 degrees Celsius, that is a compromise between yield and rate. And the pressure, 60 to 70 atmospheres, is high, but it's not higher because it's a compromise between yield and the cost of generating that pressure, and also the cost of reinforcing the machinery. And finally, you need to know the catalyst is conc phosphoric acid. You've actually done a mechanism where we've used sulfuric acid that shows the direct hydration of ethene with steam. That reaction that you're seeing is the same as what's happening here. We're going to move on and take a look at the 2 different methods of making alcohols, and I want you to take a look through and decide what the advantages and what the disadvantages are in this table. So, in the first instance, advantages. Normal pressure and 30 to 40 degrees C is a definite advantage for fermentation because that means lower energy costs, and that's never a bad thing. It's also an advantage that it comes from renewable resources. We are going to be able to carry on making it in this way. We're not going to run out of it at any time in the future. If I go to the other side, hydration of ethene is a continuous process. That's a real advantage because it can be done more quickly, more efficiently. We also get pure ethanol, which is a huge advantage compared to the impure ethanol that we would then need to purify if we needed it in industry. And finally, it's always an advantage if we get our product fast. Going through for the disadvantages, and it's the same thing in reverse really, but we've got the higher energy costs for the higher temperature and higher pressure. We've got the fact that it will run out. And for fermentation, we have the fact that it's slow, that the impure ethanol is made, and that it's a batch process. The batch process means you have to do a stage, then do the next stage, then do the next stage. And there are gaps in between. It's a very inefficient process. We're going to move on and we're going to start to look at some reactions of alcohols. So these are the objectives: looking at oxidation of primary, secondary and tertiary, identifying aldehydes and ketones, naming them, knowing how they can be oxidized. We're going to look at elimination reactions, and this is going to take us through the next 2 videos actually, the objectives that you can see here. We've got some information here about aldehydes. An aldehyde is where you have a C double bond O on the end of a carbon chain, and a ketone, the C double bond O, is in the body of a carbon chain. We also need to know that carboxylic acids have a COOH on the end of a carbon chain. Let's put it into practice and have a go at naming these compounds. Now they are aldehydes, ketones, carboxylic acids. Some of them are also alcohols. When you've tried it, unpause and we'll review. So the first one, I've got 1, 2, 3, 4 in a chain. My alcohol goes in the number 1 position. So this is 3-methyl-butan-1-ol. The second one has a C double bond O at the end of a carbon chain. That makes it an aldehyde, 1, 2, 3, 4 butanal with a 3-methyl, so 3-methyl butanal. On to the third one, we have got propanol, and it's 1, 2, 3. We can see there with our 2 methyls coming off, and you'll notice I've not numbered the ol here. That's because there is no possibility that the ol can be anywhere but propan 1-ol. And that is something that might not lose you marks, but is important, I think, to be aware of. We move down to the bottom row now, and we've got 5 carbons in a row, so it's pent. We know it's a ketone because the C double bond O is in the middle of the carbon chain. But we have to number where the ketone is. So this one is pentan 2-one, 1, 2. This one is pentan 3-one, 1, 2, 3. And finally, we have got a COOH group. That's a carboxylic acid. It's propanoic acid with a methyl group on the second carbon. Again, we don't need to number that methyl because the only place it could be a methyl group is on the second carbon. Now let's have a look at the type of isomerism that are exhibited or is exhibited by aldehydes and ketones. What do you think it is? I'm going to add a little bit more information to help you think about it. Here are propanal and propanone. They have got the same molecular formula, but a different structural formula. So they're structural isomers. Beyond that, they are functional group isomers. Some people get confused and think they're positional because I've moved the position of the C double bond O. But remember, a ketone is a ketone because the C double bond O is in the middle of the carbon chain. In an aldehyde, it's on the end of a carbon chain. So it is very much functional group isomerism that we're looking at. That takes us to the end of this video. Thank you for listening and goodbye.